Well, welcome back to POE. Today we're going to talk about speed and their graphs. We're going to measure the motion of objects to understand the relationship among distance, velocity, acceleration. Develop deeper understanding through graphical analysis of time dependence of acceleration, velocity, and distance. Today, what you're going to learn how to calculate slope from ordered pairs from a set of data collected from a graph, and interpret the data given from a distance and time graph. So these are the things we're going to be doing. First of all, let's review how to find slope from coordinates. Hopefully this is just review for you guys, but what we want to do here is up here at the top is our equation that you were taught in Algebra 1 pre-algebra from about 7th or 8th grade on, maybe even sooner. But at somewhere you were probably taught to go through here and label these ordered pairs. This being my first set of ordered pairs, so I'm going to call it x1, y1. This is my second set, so I'm going to call it x2, y2. So if I wanted to find the slope between these two, I'm going to go back into the equation, and I'm going to simply say 7 minus 1, and then 4 minus 2. And that gives me 6 over 2, which is equal to 3. So the slope of this, and this m, this little m stands for the slope. In this problem down here, again, I have x1, y1, again, because it's my first set of ordered pairs, x2, y2, so it's my second set of ordered pairs. I'm going to plug them in. I'm going to say negative 2 minus 7 over 4 minus negative 3. And I get negative 9 over 7. So that is my slope there. So there's a quick little review on how to find the slope from a set of coordinates. Okay, slopes from graphs. Let's talk about the slopes that we get from graphs. In a distance time graph, the slope is the speed. So here's what I want you to realize going forward with this, is that the slope is the speed in a distance time graph. So today, that's what we're starting to really focus in on. In our equation, in algebra, you had a great little equation that said y equals mx plus b. You guys did lots and lots of work with it. This represents the variable on the y-axis. So in our, we'll get to it in a bit here. M is the slope of the line, of your best fit line or your trend line or whatever you're trying to call it. And B basically stands for, this is the starting point of the event. So if I apply what we have, these simple equations that you guys have had now in POE or in algebra, to our y equals mx plus b, notice that there's nothing being added to these equations. So it's like we're adding 0. So in both cases you could say b is 0. Well, what's in the spot of the y? Well, that'd be the distance. So distance is in the y, so we would say y is d. R, the rate, is the slope, or you could say velocity is the slope, and that's what we had just said on the previous slide. On a distance time graph, slope is the speed, and then time is the x. Over here, if we just apply it to an equation we had earlier this year, y would be the F. That would be on the y-axis, it would be force. The mass would be the slope, and the acceleration would be on the x-axis. So let's look at what we just said here. What we've got here is a graph of distance and time. Well, we said that distance would be on the y-axis. If you look over here on the y-axis, it is indeed distance over here is on the y-axis. We had said that time was going to be on the x-axis. If we look down here, we've got time on the x-axis. And then what does that leave us with then? Well, the slope has to be the velocity. The slope has to be the velocity. Well, that's what we're saying here. This slope, all right, of the best fit line or the trend line represented here by 0.2857, is indeed the velocity. So what we've done is we've got a distance versus time graph. Distance is going to be on the y, and that's given up here because distance is said first. Time is on the x because time is given second, and that's confusing for students because they get used to ordered pairs x first, y second. But when it comes to the name of a graph, the title at the top, the first thing given goes on the y-axis, the second thing given goes on the x-axis. So another way that we could rewrite this equation, I'm going to go back to my equation up here, is what's on the y-axis? Distance. And this would be 0.2857, and instead of being x, I could put t. So what this means here is the distance is 0.2857. So it asks us a couple questions. What is the average speed of this object? Well, that's right here. We would say that it is 0.2857, and my units here are meters per second, because we took the meters and divided it by seconds to get this average speed. Where was this vehicle at the beginning of the experiment? Well, this over here is the part we haven't talked a whole lot about. That's that plus b. That is the b, we said, is the starting point. So we're starting to address now where this was at the starting point. If I start to just kind of extend this line out a little bit, you could say 0.6, 0.7, 0.8, somewhere there. I'm just going to give it a little bit of a range, 0.6 to 0.8 meters from 0. So maybe this kid had a head start or took off too soon, took off and got an extra step on everybody. What is the instantaneous velocity of the object between 5 and 6 seconds? Well, instantaneous velocity, that's going to be the slope. There's two things we've given up here now. The black line represents the average speed because it's the slope of the trend line is going to give us an average speed. That's what we said here. But the green line gives us instantaneous velocities of this person between these time intervals. As you can see, between 3 and 4 seconds, there's a certain slope. Between 4 and about 5.5 seconds, there's a different slope. Between 6 and 7 seconds, there's a different slope, and then the slope drops between 7 and 8. The slopes are representative of how fast a person is going because the slope is the speed. So right here, this person's going a certain speed. Between 4 and I'd say 6 seconds, the slope increases. It's going to be a bigger slope. So what does that tell me about the speed? The bigger the slope, the bigger the speed. If I were to just look at this, where would you say the person was going the fastest? Well, I'd look at it and say, where is the slope the greatest? And I'm going to say probably between 6 and 7 seconds. That's where the speed is the greatest. Let's go back to the question here now. What is the instantaneous velocity of the object between 5 and 6 seconds? Well, to do that, I'm going to find ordered pairs. This would be 5 and about 1.4. And this right here is going to be 6 and about 1.6. I'm going to go x1, y1, x2, y2. To find the slope, I'm going to subtract them. 1.6 minus 1.4 over 6 minus 5. And that gives me 0.2 over 1. Well, 0.2 over 1, anything divided by 1 is itself, so that equals 0.2 meters per second. And that makes sense because the average, the black line, the average has a slope of 0.2857, and the green one here between 5 and 6 is less. It's a smaller slope, which tells me that the person was going slower. Well, here we've got another graph, a little bit simpler. Says find the speed. I've kind of changed it. I had something misspelled there. Find the speed or find the velocity between 1 and 2 seconds. Well, I can't really go between 1 and 2 seconds, so I don't have a 1 second mark. So that one's kind of hard to do. But how about between 3 and 4 seconds? Well, that's here and here. This right here is 3, 150. This is 4 and 200. x1, y1, x2, y2. And now let's plug them in again. 200 minus 150 and 4 minus 3. That gives me 50 over 1. And the units are meters per second. So this right here would be 50 meters per second. Well, hey, that's where I'm going to stop today. Why don't you guys go ahead and try to do between 4 and 5 seconds yourself, and I'll catch you on the flip side.